In the last video, we saw an example of using Riemann sums to estimate an area when we were only given a table of values and not a function itself. Let's take a look at a few more examples on that page 500 in our workbook. So I've got this table here, remember, of steps to go through. The first thing to do is make sure that our table goes from the bottom to the top accurately of all of the values we're supposed to be measuring. Then we want to think about what kind of sum we're calculating and how many sums we're using. So based on the number of subintervals we're using, we're going to break the table into the appropriate number of subintervals. We want to just subtract to find the width of each of those subintervals. Using the technique that we're using, whether it's a left-hand sum, a right-hand sum, a midpoint sum, or a trapezoidal sum, we want to figure out the appropriate heights of each of the subintervals. And then based on that, we want to calculate the areas and add them together to get our total estimate. So let's take a look at problem B. So here we're approximating the integral from 0 to 15. Notice that our table goes all the way up to 25. So for this problem, I'm going to just X those last two things out. So this goes from 0 to 15 now. So how am I going to break it into intervals the same way I did up here? Well, we can think about there being 1, 2, 3, 4 gaps here. So to split it into 4 subintervals, we're going to use each one of these gaps just like that. All right, so that's how we're covering the entire area. Now our next step is we're going to calculate these widths just by subtracting. So 4 minus 0, so this rectangle would have a width of 4. 7 minus 4 is 3. 12 minus 7 is 5. And 15 minus 12 is 3. Okay, and this time we're using a left-hand sum. So remember when we were doing a midpoint sum, we looked at this interval and said, well, here's the closest thing I know to a midpoint value. And that was going to be my height. Looking at this thing, what should I use as my data for a left-hand sum for the first rectangle? Well, the left-hand value is going to be 0. So I want to use 15 as the height of the first rectangle. And in general, I really like kind of using lines to tie these together so it's really clear what I'm multiplying together. And the same thing for the rest of the intervals. So for the second interval, I'm using the 6. For the third interval, I'm using the -5. For the fourth interval, I'm using -10. And now the last thing I do is I multiply these together and I add them. So the first rectangle is going to be 4 times 15. The second is going to be 3 times 6. The fourth is going to be 5 times -5. And the last is going to be 3 times -10. And as before, you can put these into your calculator or you can just kind of add them. 3 times 6 is 18, 5 times -5 is -25, 3 times -10 is -30. And once again, you can either add these on paper, you can use your calculator, it's all good. One thing I joked with a student about earlier in the week is you kind of have to be aware that even though this is a calculus class and we're doing some very sophisticated math, a lot of the actual work we're doing is a whole lot of algebra and arithmetic this year. So it's really essential that you make sure that even if the calculator is doing the work, that you're pressing the right numbers on the calculator, because it's good at doing what you tell it to do, but if you don't put the right numbers into it, you're not going to get a good result out. One way they say that in the scientific and engineering world is garbage in, garbage out. I'm going to skip over C. I want you to practice that yourself. And the area for that is, let me give you a correct answer for that. 15, 6 plus 40. All right, so I think you're supposed to have an answer of -31 for C. All right, so just check your work for that. And D, I want to show you this because this is going to be a trapezoidal sum. And trapezoids are kind of the complicated ones. So we're going to go through our steps again. 0 to 25. Again, this is the whole table. And we're using 3 subintervals. So there are 6 gaps here. So we're going to break it down just like we did in the first problem. In fact, this is exactly the same data that we had in the first problem. So we're coming up with a second estimate for this area, except this time using the trapezoidal formula instead of the midpoint formula. Which one is a better estimate? I don't know. It depends on the actual behavior of the function, which we don't know because all we know are these specific values. Our next step is calculating the widths of these things. And now, since this is a trapezoidal sum, for this side, we need to know both parallel bases. So for 7, we're going to be thinking about both 15 and -5. For the second subinterval, we're thinking about both -5 and -2 as being our bases. And for the third trapezoid, we're thinking about -2 and 20. All right, so the last step we're going to do is we are going to calculate the area of these trapezoids here. So the first one is 1/2 times a width of 7 times 15 minus 5, plus the second trapezoid is 1/2 times a width of 8, and the bases are -5 and -2. And my third trapezoid is 1/2 times a width of 10 times -2 plus 20. All right, and this time maybe I will, let's see, so 15 minus 5 equals times 7 divided by 2. So this is 35. And the second one is -5 plus -2 times 8 divided by 2. I'm being super careful to make sure that the order of operations is being done carefully here. And the third one is -2 plus 20. I want to multiply that by 10, and we want to divide it by 2. So that's 90. All right, and so the total area we have here is 35 minus 28 plus 90, which is 97, which is making me very concerned that I made a mistake somewhere along the way here. What do I think I did wrong here? The reason I think I may have done really wrong here is because my estimate from the first one is 42. So this is a very different estimate. Does that make sense? Kind of looking at, so what I'm doing is my first estimate is taking that area, and then, yeah, I don't know. I don't know if it's right or not. I'm gonna need to pause the video right now. Google, no, My Drive, Calculus, Calc textbook, Unit 6 integration. Oh, no. I guess I didn't stop recording. Okay, so I just went and checked the teacher key because it was a very different estimate than what I got for the midpoint sum over that same interval. And I was a little concerned by that, but both of those answers are correct. And the reason is because since the table of values is so sparse, it makes a big difference which technique you use to make that estimate. So as you're doing that in the real world, you want to be really careful that you have some sort of idea. You know, if you're collecting that as scientific data, you want to have some kind of idea of what you think the things in the middle are going to look like, and then pick a technique that's going to measure that carefully. So this was odd data, and you can see that you get very different estimates depending on which technique you use. But that was the idea of it. So there's going to be a lot of homework this week dealing with problems of this sort, where you're taking tables and then putting them together to estimate integrals. So make sure that you're reading the table carefully, that you are using the right number of subintervals, that you're using the right integration technique, and that you're pulling the right values out of the table in order to make those calculations. And you'll do just fine with them.